A little more on LEDs and the interaction with the X10. The X10 system was designed back in the 70s, I believe, maybe even earlier. And we didn't have all this electronic stuff we have now. It was a pretty simple situation. We didn't have LED light bulbs. We didn't have the kind of power supplies we have nowadays, the switching mode power supplies. We didn't have any of that stuff. Well, the X10 has a zero crossing detector, and that's when it launches its data. When it sees a zero crossing, it launches its data. And I guess when they designed it, they figured that'd be the cleanest part of the wave. You know, in retrospect, to make it more compatible with today, it would have been nice if they would have made it at the crests. It probably would have survived better than it does at the zero crossing. I guess the thought is, at the peak, you know, with a motor or anything else, you're transferring a lot of power, so the impedance, I don't know, impedance might be lower at that part of the wave, who knows. So maybe they figured it would travel better at the zero crossing, but nowadays with switch mode power supplies, putting out garbage at the zero crossing, and a lot of other solid state devices likewise, and I'll show you in a second that the LED bulbs do the same thing. It's made the X10 system very problematic. The good thing about X10 is it's cheap, and I'm cheap. You know, if you've noticed all my very, very cheap equipment, because I've been poverty lifestyle most of my life. Anywho, so I go X10 just because of the cheapness. The nice thing about X10 is that its warranty, not warranty, its patent is long expired. So it's pretty much public domain in terms of usability, and anybody can make X10 devices now. So that's why it's cheap and plentiful. I'll take a step backwards. This is a diagram of an ideal voltage source, and making it a real voltage source, which is never going to be ideal. It's looking at some kind of equivalent resistance. So equivalent series resistance. If not, say I put a short across this power supply, it was ideal. I'd open the gates of God as infinite power would flow. Anywho, my idea was to put a resistor in series with the power to an LED bulb, just to raise the source impedance of the line quite a bit. I originally calculated a 200 ohm resistor, and I figured it with the bulb right in the bulb says 6 watts, 50 milliamps. So I went through and yeah, half watt resistor would just barely work. And I was going to put a variac in series just to get me back up to 120 volts. But since my issues with dimmers anyway, the 120 volts isn't that urgent. I needed an isolation transformer. A variac is not necessarily an isolation transformer. You should don't assume your variac is going to give you isolation. You have to test that, and in most cases they won't give you isolation. So instead of the variac here, I put in an isolation transformer so I could use my scope. And across here I was going to probe with my DVM and my scope. And I really don't care about the voltage, like I'm saying, because I'm using these on a dimmer circuit the whole cycle, so it doesn't seem to really make a difference whether the dimmer's on full or off or dim or whatever. It seems to perform equally poorly. Well, maybe I'll look at that later, but so that's basically my test setup. I've got a power cord, isolation transformers to the variac. I've got 180 ohm resistor, half watt, because I couldn't find 200 right off the bat. And that's it. I'm hanging the scope across these 2 points to see what I see. I was going to see if what kind of interference it generates. So the first bulb I'm looking at is the Cree bulb that gave me so much trouble in the bathroom there. And here's the Cree bulb on the scope. And you can see the obvious problem here. Right at the zero crossing line, we've got distortion. And I wonder if I could go higher in frequency and see it any differently. And here I've gotten that part of the wave by the zero crossing and blown it up as much as I could. And you can see not only is there this odd divot in the zero crossing, but it's like an oscillation that's happening before and after, a ringing before and after that glitch. Okay, now let's try the same thing with the earth bulb. I did a recent review on this bulb, got them free from Consumers Report, Energy rather. And you can see I got a totally different pattern here. I had this blown up, but the zero crossing is pretty clean. There's a little flick there. And you can see it mostly hits on the peaks, which is kind of what you'd like to see. So this bulb, you can see why it doesn't interfere with the X10 too much. I don't know why I had two of these together and they were starting to interfere. I may have to revisit that. I may have one bulb that's bad or something. Alright, I'm going to try a fluorescent bulb, but it's probably going to burn my resistor up. And here's the waveform with nothing hooked up. The bulb has been loosened up. And it's kind of interesting to see my waveform is still pretty nasty looking. But I'm going through an isolation transformer. That must be what's changing the shape of the sine wave. So this is my starting sine wave to start with. So really the earth bulb does quite nicely. Only hits the peaks and that's about all it does. Alright, I'm trying to do this with the camera still rolling. I'm going to screw in a fluorescent bulb. Stress my little resistor since it's not quite as efficient. Whoa! But again, it doesn't hit the zero crossings like that other bulb, like the Cree bulb did. It's taking energy off the peaks, really the beginning of the peak, and then it kind of... This is a, let's see if I can find the brand of this bulb. This is an EcoSave bulb. These haven't been the worst. I've had worse CFLs. My ever-present lab assistant. You guys sick of seeing my cat yet?